Hello, everybody. I would like to thank you, first of all, for working your way through this lesson today. This is quite short. I'm going to be going over part of the third lesson that's in your intro notes, the math packet that we've been working on. So we're picking up right where we left off at the end of the scientific notation, and we're looking at lesson 3, which is how we handle uncertainty in measurement. So I'm going to go through this section of the notes with you, and you're going to fill in your notes as you go. A couple of questions will pop up along the way on Edpuzzle for you to answer. And then when you finish the notes and the Edpuzzle, there are 3 questions in a worksheet, on a worksheet on Google Classroom for you to complete and submit. So this shouldn't take you very long. So if this do now question is a review of scientific notation, which we were going over yesterday in class. So converting to standard form, we need to make note of the original position of the decimal point in our number, and we also need to make note of the sign and the magnitude, or the quantity, of the exponent. So since this is a negative exponent that we're working with, which way are we going to be moving our decimal point? So since this is a negative number, we need to move our decimal point to the left 7 powers of 10, 7 decimal places. So I'm just going to rewrite this 3.62 here to give myself some more room. So I have my original location, and I just bump it 7 times to the left. And in all of those jumps, I would put in there zeros as placeholders. So that number, if I were to expand it to standard form, would look like that, which is a big pain. So that's why scientific notation is useful to us. Even without converting it back to standard form, by looking at this exponent, you should be able to tell that this is going to be a very, very small number. All right, so let's look at our information. So this lesson is all about uncertainty and measurement. When we're making measurements in science, so when you're using some sort of piece of equipment or you're recording data, there's always a limitation to how exact or how perfect our measurement can be. So again, you have the ability to pause the video, to jot things down as needed for this. When we're dealing with uncertainty, there are 2 main sources of it. One source is due to equipment limitation. So if you just write down equipment limitation, basically how good is our equipment? How precisely can we record our data? Also, that has to do with the calibration of it, meaning is it working properly? And we have somebody come in and calibrate things like microscopes and our electronic scales and other equipment. Once a year, they come in and do that for us. The other thing that can limit the certainty or the perfection of our equipment are the graduations. And the graduations are the marks that are on the piece of equipment that are used to record measurements. So things in the second lab where you looked at the lab equipment and you had to pour water from a beaker to a flask to a graduated cylinder, you should see that the graduated cylinder that I gave you was able to give you more accurate information because there's more lines on it. Think of it like a ruler. There's more lines on it that you're able to read and more information that you're able to know for certain. Another source of uncertainty in measurement then would be due to different people using the equipment. One person might estimate a reading a little bit differently. So what our goals are in science is to minimize that. We want to make things as certain as possible. So you're definitely going to want to pause here to write this down. So ways we can do that is we want to pick the right tool for the job. Now the thing with us is I'm always going to give you the right tool for the job. Fix it, calibrate it when it's necessary. Calibrate means you want to fix or make sure that it's working properly. You want to do multiple trials if necessary or if time allows, and you always want to follow your procedures consistently to make sure you're getting the most certain results that you can get. Now, with the multiple trials aspect, oh look, that's the same picture that's on your outline. Look how cute. See, graduated cylinder, lots of lines on there to read. So when we are doing multiple trials, scientists do that to be as accurate and as precise as possible. The words accurate and precise don't mean exactly the same thing. We tend to use them interchangeably, but in science they do mean different things. So the definition of accuracy is how close your measurement is to the real answer. Like, how good is your answer? So you could think of it, if you took a quiz and the maximum score you could get on a quiz was 100% and you got a 96% and you did pretty accurate work. So just think of it as how good your measurement is, how good your data is. So for an example here, if you did an experiment and you were supposed to measure out exactly 36 milliliters of some liquid, and you did the experiment and you measured out, in the first trial, you measured out 35.8 milliliters. In the second trial, you measured out 37.2 milliliters. The measurement that is more accurate is which one? Which one is closer to the real value you were trying to get? Well, that would be trial 1 because it is closer in value to the 36 that you were going for. Now, there's a calculation. This is on the next page of your outline. There's a calculation that we do in chemistry that allows us to see how accurate our information or how accurate our data is or how accurate our calculations are. And that is by calculating percent error. So you may have heard this before in another class. Math class might call it percent deviation. You're basically showing a calculation, a mathematical number to show how far off you are. We do a lot of things with percent in here. Anytime you're talking about percent, remember what that prefix, when we talked about centimeters, cent means 100. So we're looking at what the quantity is out of 100. So the first example problem that you have, the definition of this, sorry. What percent error does is it compares what a student calculated or found or measured in a lab. That's what we call the measured value, is what the person did who's doing the work. And we compare that to the accepted value or the true value. So if we did this perfectly, what we should have gotten. Or if you looked something up in a data table, like the number that you were targeting, that's the accepted value. So the calculation for this, our first calculation of the year, oh my goodness, is on reference table T. Reference table T is the last of the reference tables. It has a list of all the different types of calculations you're going to be doing this year. And so what you're going to do is you're going to take the measured value, this is on your page 2, the measured value is what you got, subtract the accepted value, which is what the true value is, then divide by that true value and multiply that answer by 100. Now, you're doing 3 different operations here. You're doing the subtraction, you're doing division, and then you're doing the multiplication. If I were you, because I'm not quite sure how GeoGebra scientific calculator goes about this, if I were you, which I'm not, but if I were, I would put in my subtraction, hit enter, then divide by the true value, hit enter again, and then multiply by 100. You don't have to write down all those steps along the way. Obviously, the calculator will store it, but I would recommend doing each of those steps independently so your calculator doesn't mess you up and do order of operations and do the division and multiplication first. That is the most common mistake that I see. Okay, so 2 examples here, and that's all we have for this little lesson. Oh, there it is. Okay. So first example, a student calculated something. All right, the student calculated it. Whatever information we have is going to be the measured value. A student calculated the percent by mass of water in barium chloride dihydrate. Do you know what this is? No, who cares? We don't care about that right now. The student calculated something to be 16.4%. But the accepted value, is 14.8%. What is the student's percent error? So for my calculation, I'm going to do measured minus accepted over accepted times 100. Show your setups. So the measured value is 16.4. That's right. This is right from the problem. There's no guessing. The accepted value is 14.8. I'm going to divide by that accepted value, and then I will multiply by 100. So if you see on a Regents question and it says, show the correct numerical setup, and it gave you this problem, you could stop right here. They want to see that you know how to set up the problem. But if it says to calculate it or find it, you have to actually plug in the numbers. So the subtraction part, the 16.4 minus the 14.8, that would give us 1.6 over 14.8 times 100, and that comes out to roughly 10.8%. So what that is saying is when the student did their work, they were 10% away from where they're, 10.8% away from what they should have gotten. And then the second example here, another data type question. The student determined the percentage of water by using the data in the table below. Fantastic. The accepted percent for water was 14.75%. What is the student's percent error? All right, well, the accepted value is 14.75. So that means that this other percentage that's in the data table, that's what the student got. So that is the measured amount. So I'm going to do my setup of measured minus accepted over accepted times 100. Measured minus accepted divided by accepted times 100. And if I simplify this numerator, I would get 1.04 over 14.75 times 100, and that comes out to about 7.0, what did I have written over here? 7.05%. So this person was 7.05% off of what they should have been. Something to make note of, in both of the examples that I just did, in the subtraction problem, it just so happened that the first number up here was larger than the second number, so this numerator was positive. So that means our answer ended up being positive. If you had a smaller measured value and a larger accepted value, the numerator would be negative, and that would make your percentage negative. That's fine. To be honest with you, most of the time when we do percent error calculations, we do the absolute value of that subtraction part. So just make the whole thing positive. In multiple choice questions, the answer choices would all be positive numbers. We tend to just take the absolute value. I'm not really sure why they don't indicate that on your reference table, but I just work here. All right, thanks for following along with this. You do have access to this video if you need to look at these examples in order to solve the 3 problems that I gave you on the worksheet on Google Classroom. So please now solve those 3 problems and submit it when you are done. That should not take you very long. Thank you very much.